Alright, time for another draftphysics.com, debatephysics.com also, but you're not allowed to debate anywhere. Pretty much just a fact. You can't get anybody to volunteer for a debate. I certainly can't pay anybody for it, can't get it as like some sort of free speech right even. Can't show up at a place like Wikipedia and make a fair argument that the page is wrong and it should be corrected. Not allowed to make that fair argument. And it just really is a terrible state for something called science to be in, frankly. Science shouldn't be deaf. Yeah, yeah, it's dumb, but it shouldn't be the deaf part. It should be able to figure out it shouldn't be deaf. All right, so we'll continue with electrodynamics, I suppose. I should do a little bit of background first, just to make a couple little points clear. All right, so the basic idea is you have a medium, a conductor, and you're going to push energy through it. And the idea is the energy basically is a pressure of an atom. And so the atoms they certainly have a shape, and what you're basically going to do is you're going to be imposing on the atoms, and you could just think of it as a shape change, and then the atom next to it's going to share that shape change. So you say this comes in with $10, you can use money, and it's going to share it with this one that's at $5, and so they're both going to agree on $7. So this one ends up at $7, but the one next to it is at $5, so it's going to end up negotiating and end up at $6. The energy is going to percolate its way through. So you can think of it as either you can take one piece of electron and you can push it into a surface really quickly. All right, so it has a lot of momentum, and then that momentum will travel by just exchanges through the wire, and it'll tend to go pretty straight because it's high pressure. And if I put in one at very slow pressure, well, then it can go sideways, and it can go this way, and it can go all kinds of ways because it's basically going to spread the pressure. So the faster it's going, the more it's going to spread the pressure forward. The slower it's going, the more likely it is to spread the pressure in all directions, all the available directions. Backwards really isn't a choice, but sideways is, and that's what basically causes the magnetism, is the surface ends up changing because of the energy you're putting through the wire. So the more atoms you can involve, the more likely it is you're going to get a magnetic effect. The fewer atoms you involve, the less likely the effect, the weaker the effect. So that's why they use low voltages to create electromagnets, because you need a lot of electrons. So the idea is, this case, you're going to push a lot of electrons, a high amperage and a low pressure. They're not as fast, but they have, there's a whole lot of them. And you're shoving them in, and you're going to move lots of electrons, and you're not going to move them as fast. And it's simple truth. All right, so in this context, they have something called a drift velocity, which is really meaningless. It just means the capacity of the wire. So it's just saying, well, how many of electrons you have and how many you're going to use. So you get a very slow drift velocity if you're sending single high voltage electrons, drift velocity really low. If you're sending a lot of low pressure and a high amperage, well, then you're going to have a very high drift velocity because they're going to use all of the electrons, and so you're not going to dilute the speed by claiming that it moved every single electron. So the drift velocity is calculated by saying what's the total number of electrons, and let's assume that this pressure moved all of them, and it doesn't. So it's useless. It's not a real information metric. It doesn't tell you anything useful. All right. So just as context. Alright, so let's move back to here, and we will. So they have a category called drift speed, so it just doesn't mean anything. The mobile charged particles, when they conductor, move consistently. So where do they figure that out? In random directions. So constantly in random directions. So yeah, if they have some thermal energy, they're going to move, but that's really irrelevant. We know that it really doesn't matter much because the colder you make it, the better it works. So the fact that it has some energy in the wrong direction is a minor amount of resistance, frankly. Like the particles of a gas, more accurately, a Fermi gas. So, who cares? Anyway, to create a net flow of charge, the particles must also move together with an average drift rate. So this is just silly. So to create a net flow of charge, the particles must also move together with an average drift rate. No, they don't. Just like a lightning bolt or anything else. The lightning bolt doesn't move all the atmosphere. The whole atmosphere doesn't go flying down. Just one little tiny section of the atmosphere gets pushed by the lightning. So it's just the same thing's happening inside the wire. You can send one little lightning bolt, or you can send a whole bunch, But they're two different circumstances. It's just silly to say every time you put electricity into a wire, the same thing happens. A different thing happens depending on whether it's a high voltage or a low voltage. And you can see it in the effect on the wires. So again, this is something I already know. I mean, you can have transmission wires at very high voltage, and it's a little tiny thin wire. But if you put 12 volts in it, and you try to run 12 volts at the same wattage, it melts like that fast. So obviously, the wire's not experiencing the same thing. The same wattage is not the same effect on the wire. So why pretend watts don't matter when watts are all you're really talking about? Is what's the total amount of movement that you're getting through the wire. And clearly, if I do the movement one way, the wire melts. If I do it another way, the wire's just fine. Electrons are the charge carriers. So again, they're force carriers. They're carrying momentum. The electrons have momentum. They're moving. They're pushing on each other. There's a real physical event taking place. It's not a magical event. It's not a synthetic event. It's a physical event. In most metals, and they flow and they follow an erratic path. So it's no more erratic than lightning. It's going in a direction primarily. And yeah, it can go a little bit sideways here and there, but basically it's going down. Alright, bouncing from atom to atom. Alright, so it's really bouncing from electron to electron. You're changing the electron pressure in the conductor. The electrons all know about each other. We all feel each other. They're all uncomfortable. It's like one guy's sitting in a chair and the other guy has his foot on the guy's head. And then the next guy has his foot on the other guy's head. And they're all sitting in chairs and they all feel the pressure from each other. Alright. But generally drifting in the opposite direction of the electric field. So I don't even know. With the opposite direction, they're not drifting in any opposite direction of any electric field. So whatever that sentence is supposed to mean, it's nonsense. The speed they drift at can be calculated from the equation. So whoever invented this useless and pointless equation, it doesn't have anything to do with anything meaningful or interesting. It's basically just telling you that if you want a really slow drift velocity, put a high voltage in, okay, at low amps. And if you want a very high drift velocity, put a low voltage in at very high amperage. It's meaningless mush. Okay. Typically, electric charge in solids flow so slowly. Okay, so obviously it flows really fast, so it's just kind of silly. Electric charges in solids flow slowly. I mean, obviously they move really, really fast, some real percentage of the speed of light. For example, in copper wire, a cross-section of 0.5 millimeters carrying a current of 5 amps, the drift velocity of the electrons is on the order of a millimeter per second. So they're assuming, okay, that at this small 5 amps, okay, on a half millimeter wire, somehow is anywhere close to the melting speed. No, it's nowhere close. So obviously it's not using all of the conductor. It's just using a small percentage of the conductor. So you're counting the drift velocity by counting how fast all the parked cars are going. So again, it's like saying what's the average speed of the moving cars in a parking lot by spreading the velocity over all the cars that aren't moving. and then saying, see how slow everybody's going. When no, the cars that are moving could be going very fast. And if you're going to spread their velocity over the cars that aren't moving, you're just going to get some stupid average that's meaningless. The speed of the non-moving electrons is not relevant. All right, to take the different example, in a near vacuum inside a cathode ray tube, the electrons travel near straight lines at about a tenth of the speed of light. I don't know what voltage that is, but yeah, they should be going maybe even faster than that. But anyway, it doesn't matter. Obviously, a significant speed, and we know that in wires the speed can get up to like 3/4, of the speed of light. So we know in a conductor, the electricity gets from point A to point B, near the speed of light. I mean, close enough where we think of it as being close enough. All right, any accelerating electric charge, so this is more of their made-up stuff about what charges are doing. And it doesn't matter about whether you accelerate an electric charge. You're not changing it, you're just moving it. Moving a charge means you change what the universe sees, okay? If my hand's over here or my hand's over here, those are two different universes that something else is going to see. And if they happen to be sensitive to where that, it's like you walking through a tree. It matters where the tree is, right? Anyway. And therefore, any changing electric current gives rise to an electromagnetic wave. So there's no waves involved. It's all about little discrete bits of energy. That's what quantum means, discrete bits of stuff. And it's not waving. That propagates at very high speed inside the surface of the conductor, outside the surface of the conductor. So the fact that there's a leach into the environment, in the sense that you can find a detectable change in the conductor, that is, the conductor will look different when you start electrifying the atoms inside of the conductor. The fact is, it just looks different. You can put your little viewer to see different things. You could see the infrared radiation, or you can see different things. But what you can't see, we can't turn into a visual effect, is the magnetic thing. But it's a clear difference. We can detect when the wire's producing a magnetic field. And it's going to produce that field out of the same energy that existed before the magnetic field. It's not excreting energy. It's just changing the way it looks. All right. Surface of the conductor. The speed usually a significant fraction of the speed of light, as can be deduced from Maxwell's equation. So, whatever. All right. It is therefore many times faster than the drift velocity of the electron. So there's no point. They say it's the drift velocity is important, but don't pay any attention because the real speed is completely different. So what's the point of this? So they're saying that some sort of field, the appearance of this wire changes before the atoms change. That's almost what they're saying. They're almost just saying that you can see the difference in the wire. You could detect magnetism before the atoms changed. No, the atoms have to change first. So your drift velocity is nonsense. The atoms change, and that changes the appearance of the wire. That creates the magnetism. I mean, they just have everything backwards. For example, in AC power lines, so they're going to use this word waves again. There's no waves of electromagnetic energy. There's no waves. It's just it's making atoms look this way, and then they look that way, and then they do this, and then they do that. Well, that's all you're doing. As you push the energy in and push the energy back, you're just changing this. It's flipping, and this flip is visible to something that can see the flip. All right. And therefore many times faster than the velocity of the electrons. So what sense does that make? The effect is going faster than the thing causing the effect. Well, no, it really can't do that. Anyway, power lines. The waves of electromagnetic energy propagate through space between the wires. So now they're arguing that somehow the energy is going between the wires. So So then why do the wires melt? I mean, that could be the obvious answer to that. Why does a wire melt if all the activity is happening outside the wire? I mean, it's just obviously bullshit. Moving from the source to a distant load, even though the electrons in the wire only move back and forth over a tiny distance. All of the effects are only over a tiny difference because you're using this alternating current. So you're changing, you're taking an like a balloon. You're pushing it in, pushing it out, pushing it in, pushing it out. You're expanding and contracting it, so it's bulging this way. I mean, is that very complicated? So the same frequency you're creating here ends up creating a frequency in this direction. I mean, it really is that simple, and they're just making something so simple so much more complicated than it needs to be stated. Just nonsense. The ratio of the speed of the electromagnetic wave, so again, the speed of the wave is the same as the speed of the electron movement, to the speed of light in free space is called the velocity factor. Wow, they have what a cool word. And depends on the electromagnetic properties of the conductor. So in some respects, that isn't true, right? I mean, aluminum wire, copper wire, they all work pretty well at creating a signal. So, and then the insulating material surrounding it, well, you have to have pretty substantial insulator to stop, a Faraday cage kind of insulator. So you'd almost have to say, yes, you have to shield it like a cable, with the complete surround of a metal container to absorb any of the signal. Okay, and on their shape and size. The magnitudes, not the natures of these three velocities, I don't even know what they're talking about there, can be illustrated by analogy with the three similar velocities associated with gases. So, too silly. All right, so you have the low drift velocity of charge carriers is analogous to air motion. In other words, winds. And again, the wind is so small compared to the pressure you're going to be creating with your voltage. All right, the high-speed electromagnetic waves is roughly analogous to the speed of sound in a gas. So there's some correlation there, but again, there's no limit to the speed of the transfer between the electrons. The higher the pressure, the less time, the force spends moving electrons. There's a certain amount of distance between them. If they move that distance really quickly, they're absorbing the force for less time, so the force is moving faster. The less movement they do to the electron, the less they're going to reduce the speed at which the force travels. Okay. They spend less time pulling the cart. So the less amount of time they spend pulling the cart, the less total reduction in the speed of the force. All right, the random motion of charges is analogous to heat. So that's the first argument, where there's already some noise in the wire, and that noise is an obstacle to the progress. So yeah, they figured that out, because you get rid of the heat, the conductor works a lot better. So not a big surprise. All right, so that's it for electrodynamics as a subject. So we'll go to something more like electromagnetism. Yeah, maybe we'll do that one. So I'll go find that page. All right, so electromagnetic induction. And they say it's not to be confused with magnetic induction, which I don't know how, they're going to be very similar subjects. But anyway, all right, electromagnetic or magnetic induction is the production of an electromotive force, EMF, across an electrical conductor in a changing magnetic field. So they're just talking about the receiving end, not the producing end, in that sense. And clearly, all you're really talking about is what do the atoms see? The atoms can be polarized. They can be, squished. And, and every time you squish one, okay, you squish it this way, it expands this way. You know, you squish it this way, it expands that way. So you're just really talking about the fact that there's this right-hand rule, this tangential perpendicular rule, that when you have a force going this way, you're going to end up with a force going one of those ways. Anyway, so Michael Faraday is generally credited with the discovery of induction in 1831, and James Clerk Maxwell mathematically described it as Faraday's law of induction. Lenz's law describes the direction of the induced field. Faraday's law was later generalized to become the Maxwell-Faraday equation, one of 4 Maxwell's equations in his theory of electromagnetism. So it's just about the effect. The fact is, if you put current through a wire, you change how the atoms look, they reflect all the energy that's hitting them, all the infrared, all the cell phone calls, all the everything that's hitting that wire now will reflect different than it would have if that wire didn't have electricity in it. So all of the energy comes from the external universe. There's no energy being irradiated out of the wire. The wire's not radiating anything because all of that energy went through the wire. Okay, so it's a side effect of moving electrons. So the side effect of moving electrons is you change the polarity of the atoms. Electromagnetic induction has found many applications, including electrical components such as inductors and transformers, and devices such as electric motors and generators. I guess they probably should put solenoids in there, but whatever. History. Electromagnetic induction was discovered, saying the same thing, published in 1831. It was discovered independently by Joseph Henry in 1832. Okay. In Faraday's first experimental demonstration, he wrapped 2 wires around opposite sides of an iron ring, a torus, so I don't know why they have to even bring that up. So it's just a continuous piece of metal. Let's see, similar to the modern toroidal transformer. Based on this understanding of electromagnetism, he expected that when current started to flow in one wire, a sort of wave would travel through the ring and cause some electrical effect in the opposite side. And the fact is it did, but it only does it when you're initiating the change and then changing. So it's only when you're changing the appearance of something can you cause something else to change. So if you do something, well, it sees that change and then it acclimates to the change, and now changing is over. You can't make changes in another wire if you're not changing this wire. So to change that one, you have to keep changing this one. So, it's that simple. You have to oscillate one to create an oscillation in the other. Okay. And oscillating in one direction doesn't work. Yeah. Okay. It looks continuous. Anything that looks continuous can't be seen as change. Okay. Based on his understanding, okay, expected the opposite side. He plugged one wire into a gavometer, okay, and watched it as he connected the other wire to the battery. He saw a transient current, which he called a wave of electricity, when connecting the wire to the battery, and another when it was disconnected. So the truth is, at first he didn't see it working, blah, 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 blah. And it was almost like accidental that they realized that when they took the experiment apart, oh, wait, something happened. Yeah. This induction was due to a change in magnetic flux. So whatever, these little special words they have for something. Let's see what it says. In physics, especially electromagnetism, the magnetic flux through surfaces, the surface integral of the normal component of the magnetic field B over that surface. So it's just the density of the magnetism. It is usually denoted with some Greek crap and whatever. Who cares? Okay. That occurred when the battery was connected and disconnected. Within 2 months, Faraday found several other manifestations of electromagnetic induction. For example, he saw transient currents when he quickly slid a bar magnet in and out of a coil of wires. So again, it's about the change you're creating. You have something that, has a dipole field, and now any atoms that can sense dipoles, that is anything that moves to adjust itself to a dipole field, will move. Single electrons won't move and single protons won't move, but something that can see the fact that the field has the both components, that is a dipole, can see it and can move. For example, he saw transient currents when he quickly the bar magnet, and he generated a steady DC current by rotating a copper disc near a bar magnet with a sliding electrical lead. And this gets into the Faraday paradox. That's the machine that, creates this whole misunderstanding because you're not rotating the actual magnetic field. If you have a piece of metal between a magnet and, your wires, well, that piece of metal isn't going to have the same magnetic field in it as the magnet, and it's not until you push the magnet right up against that piece of metal will the metal have a magnetic field that's consistent with the magnet. Alright, Faraday explained electromagnetic induction using a concept called lines of force. So this is where things really get messy, because Maxwell uses terms like field, the difference between a line of force and a field line. And Faraday basically says lines of force are field lines. So he doesn't make that distinction. So this is where, the precision of conversation or verbiage or what use, it's like the whole Newton thing using, quantity of motion versus the explicit word of velocity. And you're saying, well, what are you talking about? You're talking about velocity or you're talking about momentum? So language gets messed up, unfortunately. But there's a big difference between field lines and lines of force. So let's see what they say for lines of force. Line of force in Faraday's extended sense is synonymous with Maxwell's lines of induction. So the lines of induction are not the lines of force. Okay, Faraday usually discusses lines of force as chains of polarized particles in a dielectric, yet sometimes Faraday discusses them as so you can just see there's a little bit of a distinction between the two ideas. The idea would be is the lines of force are the actual, what's the force doing? And the force is just straight lines coming perpendicular off a charge or off a charged surface. They're straight lines of force potential, momentum, you could argue. And field lines are where there's an equal potential. So if you put a compass in there or you put something in there, it'll detect the force and tell you whether it's this much that way or this much that way. And so you can detect how strong the two forces of the dipole are. But those are not real lines. There's no path. The field lines aren't real things. They aren't real pathways. The lines of force are real. They're like the photons radiating out of the sun. They're real straight lines, real rays. So I guess you could say it's the difference between understanding the rays of force versus the I still don't know what to call those little idiotic lines that a magnet makes. In when you sprinkle the iron filings, those lines are not indicating anything that's real. It's not a real pathway of some kind. And Faraday thought they were. However, scientists at the time widely rejected his theoretical ideas. Well, he had a lot of dopey ideas, frankly. So if you go back and look at his notes and his letters, he was arguing for all kinds of gears and all kinds of different things inside of material objects. And, look, I've drawn things that didn't work either. So, I'm not finding fault. I'm just saying that, what they decide is the truth out of all the stuff that's speculated. That's the whole thing that's being criticized here. is that these things that are accepted as the truth aren't very well tested. And some of the bad ideas end up being put in the good pile. All right, mainly because they were not formulated mathematically. That's even sillier. An exception was James Clerk Maxwell, who used Faraday's ideas as the basis of his quantitative electromagnetic theory. In Maxwell's model, the time-varying aspect of electromagnetic induction is expressed as a differential equation, which Oliver Heaviside referred to as Faraday's law, even though it is slightly different from Faraday's original formulation and does not describe motional EMF. So I imagine they're talking about it doesn't describe the moving magnet thing or something. I don't know. Heaviside's version is the form recognized today in the group of equations known as Maxwell's equations. So this whole thing is just so messy. I mean, Maxwell took pieces of other people's stuff, put 14 equations together. They were reduced to 4 equations. I mean, who knows who did what? It's really pretty messy. And they just call it, Maxwell's equations when, well, they aren't exactly what Maxwell wrote. Anyway, in 1834, Hendrik Lentz formulated a law named after him to describe the flux through the circuit. And Lentz's law gives the direction of the induced EMF and current resulting from electromagnetic induction. So the fact is, it does tend to push north-south, pushes a certain way, and that way means there is a right-hand rule. And I guess I would argue that that's because the electrons themselves don't move perfectly perpendicular in the atoms, so the atoms are pointing in a direction. So, but yeah, I'll get to that in some other video. Faraday's law of induction makes use of magnetic flux. So again, whatever, I mean, it's just kind of a mush word, flux, whatever that is. It's an actual change in the field, and the field is changed density-wise based on how many atoms you involve are polarized. So the more little magnets you make inside of it. So the more you can magnetize a piece of steel a lot or a little, depending on how rigorous you are in creating the magnetism. That is, ideally you create a very strong magnetic field and then you vibrate the piece of steel and all of the little domains will line up. But if you do it by just scraping it on a magnet or do it some other way, you're not going to get nearly as much magnetism into the steel. That is, you're not going to polarize the atoms in the same direction as completely. All right, back. The magnetic flux is defined by a surface integral. So they show this loop of wire, okay, but part of the argument to be made is that if you have a great deal of space between these loops, okay, that's going to hurt the strength of your field. Because what you're really doing is creating a tube. You're creating a tube, and inside the tube, it's all reflections. So that's what's magnifying the magnetic effect, is the fact that you're trapping the force inside of that tube. So in some ways, this is a rudimentary version of a laser, in the sense that you're allowed to take the energy and concentrate it inside the tube. And so there's a lot more of it inside the tube because it's reflecting off the interior surfaces. Alright, where dA is an element of the surface enclosed by the wire loop. Okay, so that's the part where you have to measure the thickness of the wire versus the spacing between the loops. And ideally, you don't have any spacing between the loops. B is the magnetic field. D is the dot product, corresponds to an infinitesimal small amount of magnetic flux. And that's on the outside. In the more visual terms, the magnetic flux through the wire loop is proportional to the number of magnetic field lines that pass through the loop. So the point is that all this stuff is just radiated straight line energy. And you could draw a diagram of all the straight lines, the actual lines of force are behaving. And so obviously inside the wire, lots of reflected energy. Outside the wire, no reflected energy. When the flux through the surface changes, Faraday's law of induction says that the wire loop acquires an electromotive force. Most widespread versions of this law state that the induced electromagnetic force is a closed circuit is equal to the rate of change of the magnetic flux enclosed in the circuit. So again, they really just don't even talk about the fact that all you're really doing is taking a long wire, putting it in a small amount of space, and creating a concentration of the effect of the magnetism. So if you spread the magnetism, if you took a row of magnets and you spread it over a large distance, the amount of force it's going to create is reduced. But if you take all those magnets and compress them in a small amount of space, then you're going to have a lot more magnetism. And so all you're really doing is saying, how much signal can I create by concentrating, okay, the surface. Let's see. All right. So when the flux through the surface changes, Faraday's law of induction says that the wire loop requires an electromotive force. The most widespread version of this law states that the induced electromotive force in any closed circuit is equal to the rate of change of the magnetic flux enclosed inside the surface. Yeah. Just much more complicated than it needs to be, but obviously the stuff enclosed just means the reflections on the inside. All right, you're concentrating the vibrations by keeping them inside the object. The direction of the electromotive force is given by Lenz's law, which states that the induced current will flow in the direction that will oppose the change which produced it. So how to say this? Obviously, if you're reflecting north against north, you know, a north effect pushes. The electrons push they're going to create an opposite effect inside of whatever they're. If you're pushing out, you're going to push in on the other guy. Okay, that's the tendency. All right, so you end up creating a magnet that has the opposite polarity of the one that initiated it. But, so there is a but here. Yeah. So this gets into they probably should just save this as a conversation about the difference between ferromagnetic and paramagnetic and whatever the other thing is. Because that's a effect where the magnetism you're creating is the same polarity as the magnet initiating it. And that's where it gets, that's where you get into the resistance. So you could argue, I think you could argue that the paramagnetism is the only part creating the resistant part. And the rest of it is conducive. But anyway. This is due to the negative sign in the previous equation. To increase the generated EMF, a common approach is to exploit flux leakage by creating tightly wound coil of wire. So at least they're getting to that point where, yes, it's more efficient if the wire is tightly wound, composed of n identical turns, which is the same magnetic flux going through them. The resulting EMF then is n times that of a single wire. All right, generating an EMF through variation of the magnetic flux through the surface of the wire loop can be achieved in several ways. Okay, so the magnetic field B changes, so that has to be alternating. The wire loop is deformed and the surface changes. Well, that's a little weird. The orientation of the surface changes. Any combination of the above, so you could spin it, I guess. But that's mechanical then. You're just conveying a mechanical change. So it's not really the same as conveying an electrical magnetic field change. All right, in general, the relations between EMF and wire loop encircling a surface and the electric field in the wire is given by, so another integral. So I don't know how, doing math is not much fun. Anyway, so Faraday's law describes two different phenomena. The motional EMF generated by a magnetic force on a moving wire, So you're really just showing it a moving pattern. So all you have to do is create a moving pattern. So you have red, blue, red, blue. You can move the entire thing with the red, blue on it. I guess you can move a whole magnet and change the pattern, right? Or you can put electricity through it and have it change red, blue, constantly changing. So you have two choices of how you change what this section of space looks like. You can move the whole object, or you can have the pattern change on the surface. All right, Faraday's law describes two different phenomena. The motional EM generating magnetic force moving in the wire, and the transformal EMF that is generated by an electric force due to the changing magnetic field. So it's both the same thing. You're changing the field by moving the whole magnet, and you're changing the field by changing the pattern on the surface of a wire. Due attention to the separate physical phenomenon in Maxwell did. In 1861, this is believed to be the unique example in physics where such a fundamental law is invoked to explain two such different phenomenon. So I don't see anything too spectacular there. So there's a 30-year period between Maxwell and Faraday. Faraday was getting pretty old by the time Maxwell spoke to him. All right, Einstein noticed that the two situations both correspond to a relative movement between the conductor and the magnet. So this is where they try to pretend, that relativity has something to do with it, or that there's not an explanation for why you can induce the field by moving one object, but you can't induce the field by moving the other object. And again, I would argue that the only problem is how you engineer your experiment. And this is back to Professor Lewin and probe wires. Induced fields are really difficult to sample because you have to go inside the induced field. You have to get radiated to measure the radiation. Yeah. And so it kind of breaks the game. And the outcome was unaffected by which one was moving. This was one of the principal paths that led him to develop special relativity, which doesn't make any sense, frankly. But the very fact that he contemplated the fact that it makes a difference which thing is moving, and it only makes that difference because you have to know that your probe wires are in a different field when one's moving than when the other one's moving. Your probe wires are in a different field. So it's all about probing the experiment, which you can't do. And they'll just keep on saying that that this somehow is about electricity traveling through the disk when it's really just about the wires that you're using to sample your disk are in the frickin' experiment. All right, the EMF generated by Faraday's law of induction due to relative movement of a circuit and a magnetic field is the phenomenon underlying electrical generators. So the simple principle is obvious enough. You're just changing a pattern. You can change it by moving a solid magnet, or you can change it by just moving the electrons inside of the material. When a permanent magnet is moved relative to a conductor or vice versa, an electromagnetic force is created. If the wire is connected through an electric load, current will flow, and thus electrical energy is generated. That's such a piece of infantile mush there. Obviously, if a load is connected, yeah, that's right. You can't keep flowing the electricity if there's nowhere for it to go. Anyway, converted the mechanical energy of motion to electrical energy. Okay, for example, a drum generator is based upon the figure to the bottom right. A different implementation of this idea is the Faraday disc, shown simplified on the right. So, yeah, and it's really is simplified. So let's see how to explain. They don't even point that this is a magnet. The B field coming out here. This is the magnet. And you're rotating the discs. Yeah, I don't know. It's a pretty bad drawing. But you can definitely see that you have to sample it somehow. Somehow you have to sample it. And by sampling it, you're going inside the magnetic field to sample it. All right. In the Faraday disc example, the disc is rotated in a uniform magnetic field perpendicular to the disk, causing a current flow in the radial arm due to the lens force, says you. Okay, mechanical work is necessary to drive this circuit. When the generator current flows through the conducting rim, the magnetic field is generated by the current through the Ampere's circular law. Yeah, labeled B. Yeah, whatever. The rim thus becomes an electromagnet that resists rotation of the disk. On the far side of the figure, the return current from the rotating arm, so the current they're going to have going in the wrong direction, of course, through the far side of the rim to the bottom brush. The B field induced by the return current opposes the applied field. Really is no point in reading this, right? This is the kind of thing where you have to draw it and show it. So we'll wait. I think there's an Action Lab video on the Faraday paradox, and that's probably a better thing to use to explain when you can, when you can use induction and motion, and when it doesn't work. Okay, when an electric current or loop of wire changes, the changing current creates a changing magnetic field. So again, the magnetic field is merely a visual effect. So you're just changing how the universe reflects off the object. You're changing what it looks like. That's it. That's the only force involved. You're just changing a force that looked purple, and you're changing it into little blue and red bits. You're changing its appearance. The second wire in reach of the magnetic field will experience this change in magnetic field as a change in the coupled magnetic flux. Therefore, an electromagnetic force is set up in the second loop called the induced EMF or transformer EMF of the two ends of a loop are connected through an electrical load. Current will flow. I don't know. Not very interesting. Current clamp. Well, we won't bother with that. Magnetic flow meter. So I don't think that's going to be interesting either. I don't know if eddy currents are all that interesting because they're not something we can see. So you could add that eddy currents are like stress in some kind of material that's compressing something that's like a spring. So if I take something and I clamp it and I have a spring, and let's say the clamp's made out of plastic, the whole time it's compressing it, there's a flow of stress, okay, of motion, little tiny motions happening inside the material. The material is actually doing work to hold the spring in position. So it's constantly fighting with that pressure, constantly having to do a loop of work. And it's just doing it with electrons. And because electrons are non-frictional, it's not losing any energy to do it. So the atoms aren't going to fall apart because of it. All right. So I don't know if that's, Again, these are all subjects where you need a little bit more than the drawings they provide to do anything, really interesting. So then they just talk about how you can, you can take advantage of laminated transformers because it gets rid of all the back EMF, the opposite magnetism you end up creating. So if you do it with a number of layers instead of one solid piece of metal, it works better, blah, blah, blah. So, then the parasitic stuff has to do with timing. The fact is as you're spinning it, it's different amounts of time. You want kind of a resonant thing to happen. You want your forces to always be applying a positive force. So you never want to have you want it to be pushing and pulling, so to speak. You want the positive electron retraction, if you want to call it, versus the electron pushing out. You want those two events to perfectly match when you're hitting those different fields. And all of that makes the motor more efficient and all of that kind of stuff. But yeah, going into a bunch of motor stuff without drawings is probably not a great idea. So they really didn't say much about what an electromagnet is. They didn't go into it's electromagnetic induction. So this is really, radio. in some respects, and they didn't talk about radio at all. So they didn't really talk about the fact that the induction is a field of energy that you've changed because you've changed the pattern. The energy's hit something, caused it to reflect in a different way, and now that difference can be detected by something else that can see the difference. All right. Yeah, so we'll call that a video. And move on to the next bit, which I guess it's a separate subject. Electromagnetism is separate than electromagnetic induction, so maybe we'll go with that subject. Yeah, that might be better. Okay, so we'll try that next time. All right, so anyway, till the next time and such and so forth and whatnot.